Hi, welcome again. I'm Neil. This chapter is all about photography. Well, sort of. It's about images, how to capture images. Microscopes, telescopes, binoculars, cameras, the human eye. All of these have something in common. They need to capture light emanating from an object and form an image. For example, on one of my trips to the Southern Hemisphere, this is Antarctica, I captured a stunning image of the reflection off of these glaciers and snow-capped peaks in Antarctica, reflecting off the very calm waters of the Southern Ocean. Such a beautiful picture. It captures both shadow and sunlight. How does this work? Well, the reader might be interested to know that it's actually quite simple. It's just two beams of light from an object need to be captured to form an image. Now, images are captured many different ways. Lenses, mirrors, refracting surfaces. For example, if we were to scroll through this chapter, we see that mirrors capture images by creating a virtual image. It is not real. Light from an object reflects off of the mirror surface, and it appears as if the object is located behind the mirror itself. Obviously, there's no image there. For example, if you're standing in front of your mirror looking at yourself, you'll notice a few things. Your right hand is actually the image's left hand, and vice versa. It also seems that the image of yourself seems to be equidistant from the mirror as you are. That is to say, the image distance is behind the mirror at the same magnitude as you are standing in front of the mirror. Now, if you were to place a camera or a screen, for example, where your image appears to be located in the wall behind the mirror, it would capture nothing because nothing is there to be captured. No light rays actually emanate from inside the wall, obviously. So this is an example of a virtual image. Plane mirrors with no curvature, like these shown here, can only produce virtual images where the image appears to be on the opposite side of the mirror as the object itself. And it also creates a lateral reflection, that is a 180 degrees sideways reflection. This is why your left is your right and your right is your left with your mirror image. Now, as we go through much of this chapter, it's about some fantastic images and how they are possible. This one is taken in Fiordland National Park. I took this picture because it was quite fascinating. With the Southern Alps, a huge mountain range in the southern island of New Zealand, all of it captured in a very small alpine lake. Now, how is that possible to capture such a huge mountain range in a small body of water and it be so crystal clear? Well, the answer lies in this chapter, and the reader's going to find out. So, as we scroll further down, this is taken in Tromsø, in Norway, inside of the Arctic Circle. These are reindeers, and the reindeer's images are also captured, reflecting off the calm waters of the Antarctic Bay. The reindeers can see their own images, so they also see what you see. It's like looking into a mirror. Their left is the image's reflections, right, and vice versa. Now, how do we calculate all of these parameters? The height of the object, the height of the image, the magnification, is it diminished, is it upright, is it virtual, is it real? Well, this chapter deals with all of these. So one important thing is to realize that if you ever pay attention to a satellite dish or a large radio telescope, you would notice that they're always parabolic in shape, never circular. And this is why. This diagram shows a parabolic mirror, could be a radio telescope, and a circular one. And if you would notice in the circular mirror, incoming beams of light as they reflect off of the perfect circular shaped mirror, the light rays never coincide at a single point. There is no true focal point. So the image at best would be blurry. Parabolic mirrors, however, you can see that all of the incoming rays reflect to the same one congruent point, the focal point. So it is possible to form a clear, crisp image with a parabolic mirror, but not with a circular mirror. As we go further down, it's shown here that if we put some curvature onto this plane mirror, we can create either a concave or a convex. Convex means the mirror surface bulges towards the object. Concave means the mirror's surface indents away from the object. Now, concave mirrors and convex mirrors, these are curved mirrors, and they also can form virtual and real images, and it depends on several things. For example, we see here that a plane mirror can only form a virtual image because the image distance is negative, meaning it's on the opposite side of the mirror as the object itself. Convex mirrors, same story, they can only form a virtual image, but concave mirrors are interesting because they can form either a virtual image or a real image, depending on where the object is located, as we shall see later on in this chapter. Here also is the introduction of the mirror equation. The mirror equation relates the focal distance, that is the distance from the focal point where an image is formed, to the mirror surface, that's the focal distance. So the mirror equation relates the object distance, p, the image distance, I, and the focal distance, f. So it's a very useful equation. We're going to get a lot of use out of this. So this is called ray tracing, and notice it takes just 2 ray diagrams of the light emanating from an object to find where its image is going to be located, if indeed at all an image can be formed. In some cases it cannot. We see here that if the object is placed inside of the focal point of a concave mirror, the image, it is virtual, but it is magnified and it is upright. And there are several other examples. We see here if the object is outside of the focal point, again for a concave mirror, we see that the image formed is real. It's on the same side of the mirror as the object, but it is inverted as well as magnified. So the point being, just 2 ray diagrams are always needed to form the image, and many of the diagrams in this chapter are just that. It's ray tracing. This one is a special case of the object located at the focal point of a concave mirror. The reflected rays are parallel, which means they never converge at a point to form an image, so no image can be formed for an object placed at the focal point. And that's the essence of this entire chapter. It's all about how to form images. Now, we also talk about lenses. Lenses can take on different shapes, convex, concave, for example, and they all form positive or negative image distances, which means the images can be either virtual or real depending on where the object is located. So once the reader has a chance to go through all of the ray diagrams, this is what the entire chapter is about. It'll give a good understanding of how to create images. All right, and there are several examples to consider at the end of the chapter, and the reader should find this very enlightening, I believe, in the formation of images, in particular if you're into photography. I thank you for your time. Bye-bye.